In the last video, we watched a language model grow, from a slate of random numbers and an ocean of text through a trillion rounds of predicting the next word. A vast intelligence emerged. We called the result a base model, and it is genuinely brilliant. It has absorbed a huge fraction of human knowledge, so let's do the obvious thing. Let's ask it a question. You type, "What's a good way to learn the guitar?" and a helpful, well-behaved assistant would answer. But the raw base model, it might reply with, "And how long does it take to get good? What song should I start with? Is it better than piano?" It just continues your text with more questions, because in its training data, a question like yours was often followed by a list of related questions. It didn't answer you. It doesn't even seem to understand that it was supposed to. This is the strange and crucial gap. We have, sitting in front of us, a system with immense latent intelligence that has no idea it's meant to be a helpful assistant. It's a genius with no manners, no mission, and no instinct to actually help. All that capability, and it won't answer a simple question properly. Something has to bridge that gap. That something is fine-tuning. It is the process that takes this wild, brilliant, unsteerable base model and shapes it into the helpful, honest, safe assistant you actually talk to every day. If pre-training grew the mind, fine-tuning gives it a purpose. And the way it does that is a genuinely fascinating story, involving human teachers, a second AI that learns our taste, and some beautiful, subtle ideas about how to align a machine with what people actually want. This is the second half of how the model you talk to gets made. We'll go deep. Supervised fine-tuning, reinforcement learning from human feedback, the reward model, the dangers, and the modern shortcuts. By the end, you'll understand exactly how a document completer becomes a helpful assistant. Let's build it. Chapter 1, what we start with. Before we can shape the base model, we have to be crystal clear about what it is and what it isn't, because everything about fine-tuning is built on top of it and only makes sense in light of it. What the base model has is staggering: deep knowledge across nearly every domain, fluency in dozens of languages, the ability to write code, to reason step by step, to summarize, to translate. All of that capability is already in there, fully formed at the end of pre-training. Fine-tuning does not add any of it. Let me say that again, because it's the single most important idea in this video. Fine-tuning does not teach the model new knowledge or new skills. The intelligence is already there. What the base model lacks is any sense of how to use that intelligence for you. It has no instinct to follow an instruction rather than just continue it. No notion that a question deserves an answer. No sense of when to refuse a harmful request. No consistent personality or tone. It is pure, undirected capability, a reservoir of intelligence with no channel to flow through. So the right mental image for fine-tuning is not teaching, but sculpting. The base model is a huge block of marble, already containing every possible statue. Pre-training quarried that block, and it was astronomically expensive. Fine-tuning is the sculptor chipping away, revealing the specific, useful shape that was latent in the stone all along. We're not adding marble, we're shaping what's there. So we start with a reservoir of raw ability and no direction. The task is to give it direction without damaging the ability. But direction toward what, exactly? Before we can shape the model, we need to be precise about the target we're shaping it toward. Chapter 2, the target. If we're going to sculpt the base model into a good assistant, we need a clear definition of good, and the field has largely converged on three words, often called the three H's: helpful, honest, and harmless. Almost everything fine-tuning tries to achieve lives under one of these three. Helpful means the model actually does what you're asking. It follows your instruction, it answers your question, it stays on task, it gives you something genuinely useful. This is the one that fixes the problem we opened with, the base model that answered a question with more questions. A helpful model recognizes an instruction as an instruction and responds to it. Honest means the model tells the truth as best it can, and crucially, admits when it doesn't know. This one directly targets the hallucination problem from the pre-training video. An honest model, faced with something outside its knowledge, should say "I'm not sure," rather than confidently inventing a plausible-sounding answer. Teaching a model to know and admit the limits of its own knowledge is one of the hardest parts of all of this. And harmless means the model refuses to help with genuinely dangerous or malicious requests, avoids toxic and biased output, and generally doesn't cause harm. This is the safety dimension, closely tied to the guardrails we discussed in the Agent series. It's the model learning where the lines are and holding them. And here's what makes it genuinely hard. These three are constantly in tension. The most helpful possible answer to a dangerous question would be harmful. The most harmless model would refuse everything and be useless. Perfect honesty might mean admitting ignorance so often it feels unhelpful. Fine-tuning isn't about maximizing one of these. It's about finding a wise balance among all three, and that word balance will haunt this entire video. So the target is clear, a model that is helpful, honest, and harmless all at once in balance. Now, how do we actually move the base model toward that target? It turns out the basic machinery is something we've already seen. Chapter 3, the basic mechanism. Here's the reassuring part. At its core, fine-tuning uses the exact same machinery as pre-training. There's no new fundamental algorithm to learn. If you understood the last video, you already understand the engine. Remember the loop, show the model some text, have it predict the next token. Measure the loss, the surprise, with that same cross-entropy formula, the negative log probability of the correct token. Compute the gradients by backpropagation, and nudge the weights downhill with gradient descent. That entire loop is exactly what fine-tuning does too. We are simply continuing to train the model, using the same update rule as before. So if the machinery is identical, what actually makes fine-tuning different? Two things, and they're both about the data. First, the data is tiny by comparison. Pre-training used trillions of tokens. Fine-tuning might use just thousands or a few million carefully chosen examples. Second, and more importantly, the data is curated. It is not a raw scrape of the internet. It is a small, high-quality collection of exactly the kind of behavior we want the model to adopt. And because the dataset is small and the model is already fully formed, fine-tuning is a gentle nudge, not a rebuild. We use a much smaller learning rate, that eta from the update rule, so each step barely moves the weights. We're not trying to reshape the model's knowledge. We're delicately adjusting its behavior, its habits, its defaults, while leaving that hard-won intelligence almost entirely intact. Big enough a nudge to change how it acts, small enough to preserve what it knows. Same engine, tiny curated data, gentle touch. That's fine-tuning in the abstract, but it comes in distinct stages, and the first stage is the one that does most of the heavy lifting. It's where we simply show the model what good behavior looks like. Chapter 4, Supervised Fine-Tuning. This first stage is usually called Supervised Fine-Tuning, or SFT, and sometimes Instruction Tuning. The idea could not be more intuitive. If you want the model to behave like a helpful assistant, you show it thousands of examples of a helpful assistant behaving well. It learns by imitation. What does the data look like? It's a collection of demonstrations. Each one is a pair. A prompt, the kind of thing a user might ask, and an ideal response, an example of exactly how a great assistant should answer it. A human writes or carefully curates the response. Explain photosynthesis to a 10-year-old, paired with a warm, clear, age-appropriate explanation. Thousands upon thousands of these prompt and ideal answer pairs, covering a huge range of tasks. Then we train, we show the model the prompt, and we have it try to predict the ideal response, token by token, using the very same next token prediction loss. When it deviates from the ideal answer, the loss is high, and the gradients nudge it closer. Do this across thousands of high-quality demonstrations, and the model gradually absorbs the pattern. When I see a prompt like this, I should produce a response like that. And the effect is remarkable and fast. After supervised fine-tuning, that same base model, the one that answered a question with more questions, will now, given what's a good way to learn the guitar, actually give you a clear, structured, helpful answer. It has learned the format and the habit of being an assistant. This single stage does most of the work. It's the difference between a document completer and something that genuinely feels like a helpful chatbot. So supervised fine-tuning, learning from demonstrations, gets us most of the way to a helpful assistant, surprisingly quickly. But most of the way is not all of the way, and to understand why we need more, we have to look closely at what imitation can and cannot teach. Chapter 5, What Imitation Really Teaches. It's worth pausing to be precise about what supervised fine-tuning actually changes, because it's subtler and more interesting than it first appears, and it clears up a very common misconception. Supervised fine-tuning does not mostly teach the model new facts. Remember, the knowledge was already there from pre-training. What it teaches is a role. It's like taking that brilliant but aimless graduate and giving them their first day of training as a customer support agent. You're not teaching them new facts about the world, you're teaching them how to behave. When someone asks a question, answer it, be clear, be polite, stay on task. The knowledge was always there. The demonstrations activate a particular way of using it. Another way to see it, the base model already contains, somewhere in its vast range of possible behaviors, the behavior of a perfect assistant. It also contains the behavior of a rambling forum poster, a spammer, a novelist, and everything else it ever read. Supervised fine-tuning doesn't create the assistant persona, it finds it and makes it the default. It shifts the model so that helpful assistant is the behavior it naturally falls into, instead of one possibility among millions. This is also where the model learns the very shape of a conversation, the turn-taking structure, that there's a user and an assistant and special markers separating them, that the assistant speaks and then stops and waits rather than continuing to write both sides of the dialogue forever. All the invisible scaffolding of a chat is installed here, in supervised fine-tuning. So imitation gives the model a role, a persona, and the structure of conversation by showing it what good looks like. It's powerful and it's most of the battle, but imitation has a ceiling, a real and fundamental limit, and understanding that ceiling is the key to everything that follows. Chapter 6: The Ceiling of Imitation. Supervised fine-tuning is learning by copying human-written examples, and that approach, powerful as it is, runs into three hard limits that no amount of more examples can fully solve. The first limit, you can only imitate what someone can actually write down. For many of the most important qualities we want, like just the right amount of caution, or the perfect balance between thorough and concise, it is genuinely hard to produce a single, definitive ideal answer to demonstrate. Good is often a matter of degree and of taste, and you can't always capture that in a written example. The second limit is deeper, and it's the crucial one. For most tasks, it is far easier for a human to judge two answers than to write the perfect one from scratch. Ask me to write the ideal response to a subtle question, and I'll struggle for an hour. But show me two responses and ask which is better. I can tell you in seconds. We are much better critics than authors, and supervised fine-tuning only uses us as authors. It completely wastes our much stronger ability to judge. And the third, by pure imitation, the model can, at best, become as good as the human demonstrations it copies. It's trying to match the examples. It has no mechanism to become better than them, to discover a response that's actually preferred over what any human wrote down. Imitation aims at the level of the teacher. To go beyond it, we need a fundamentally different kind of signal. So imitation is limited by what we can write, wastes our talent for judgment, and can't exceed its own examples. What we need is a way to teach the model using comparisons, using our ability to say this one is better than that one. And that shift from demonstration to preference opens the door to the most influential idea in modern alignment. Chapter 7: The Alignment Problem. Let's name the real challenge directly. We want to install behavior that is subtle, nuanced, and hard to specify, be helpful but not sycophantic, be cautious but not useless, be honest but kind. How do you get a machine to do something you can feel is right, but can't cleanly write a rule for, or even a perfect example of? This is the alignment problem, and it's one of the central challenges in all of AI. You can't write a rule for good judgment. If you try to specify every do and don't, you'll end up with thousands of contradictory rules and still miss endless edge cases. And as we just saw, you can't always demonstrate it either, because the ideal answer is hard to write. Both of our obvious tools, rules, and demonstrations hit a wall on exactly the qualities that matter most. But there's a third path, and it flows directly from that insight about judgment. You can't easily write the perfect answer, but you can almost always compare. Shown two responses, a person can reliably say which one is better, even for these subtle, hard-to-articulate qualities. That single ability, the ability to compare, turns out to be a powerful enough signal to align a model. We just need a way to turn a pile of these comparisons into a training signal, and that is exactly what the next technique does. The technique has a name you've probably heard: reinforcement learning from human feedback, or RLHF. It's how models learn to be not just capable, but genuinely pleasant and aligned to talk to. And it comes in 3 distinct steps. Let's build them one at a time, starting with the humans. Chapter 8, RLHF, Step 1, Collecting Human Preferences. The whole technique rests on that one insight: people are better at judging than writing. So the first step is to systematically collect a large number of those judgments and turn human taste into data. The process is straightforward. Take a prompt, have the current model generate 2 or several different responses to it. Remember, the model is random, so the same prompt gives different answers each time. Then show those responses to a human labeler and ask a simple question. Which of these is better? The human picks, and that single choice, response A is better than response B, is recorded. That's it. That's one piece of preference data. Now do that on a massive scale. Thousands upon thousands of prompts, each with responses ranked by real people, according to guidelines about what helpful, honest, and harmless actually mean. The result is an enormous dataset of human preferences, not ideal answers, but comparisons. A vast record of between these two, people preferred this one. We have captured in data a fingerprint of human judgment. But there's an immediate practical problem. Human feedback is slow and expensive. During the actual training we're about to do, the model will generate millions upon millions of responses, and it needs a judgment on every single one instantly. We cannot possibly have a human rate all of them. It would take lifetimes. We need something that can judge like a human, but at the speed and scale of a machine. And that is the ingenious core of the whole method. We have a rich dataset of human preferences, but humans are far too slow to guide the training directly, so we do something clever. We use that dataset to train a second AI whose entire purpose is to imitate human judgment. We're going to build ourselves an automatic critic. Chapter 9, RLHF, Step 2, the Reward Model. This is the pivotal idea, so let's take it slowly. We are going to train a separate model called the Reward Model, whose only job is this. Look at a prompt and a response and output a single number, a score, predicting how much a human would like it. A high score for responses people prefer, a low score for ones they don't. And how do we train it? Using exactly that preference dataset we just collected. For each comparison where a human said A is better than B, we train the reward model to give a higher score than B. We show it hundreds of thousands of these human judgments, and it gradually learns to predict them. It's learning to internalize the pattern of human taste. In effect, it's answering the question, what do humans tend to prefer, and can I score any new response accordingly? We can write what it's learning quite cleanly. If the reward model gives response A score RA and response B a score RB, we want the probability it assigns to a being preferred to look like the softmax, the sigmoid, of the difference in their scores. Trained across all the human comparisons, the reward model becomes a smooth, automatic stand-in for human judgment. Give it any response, and it returns a number estimating how much a person would have liked it. And this should sound familiar. It's the same idea as the AI judge from the guardrails and evals videos. A model trained to evaluate another model's output the way a human would. Here it plays a starring role, because now we have something priceless. An automatic critic that can score any response instantly, millions of times, approximating what a human would have thought. The slow, expensive human judgment has been distilled into a fast, tireless machine. So now we hold a reward model, a learned proxy for human preference that can score any response on demand. The pieces are in place for the final and most powerful step. We let the model practice, and we use the reward model to tell it millions of times when it's doing well. Chapter 10, RLHF, Step 3, Optimizing Against the Reward. Now the actual reinforcement learning begins. Up to now we've been gathering judgment and bottling it into a reward model. Here's where we finally use it to change the assistant, and the loop is beautiful. The model, which in this context is called the policy, is given a prompt. It generates a response. The reward model scores that response instantly, and then we update the policy using gradient descent to make responses that earn high scores more likely and low-scoring ones less likely. The model generates, gets graded by the reward model, and adjusts to score better next time. Round and round millions of times. It is, quite literally, practicing to please the reward model, which is itself a stand-in for us. And here's why this transcends the ceiling of imitation. The model isn't copying human answers anymore. It's exploring. It can generate a response no human ever wrote, and if the reward model scores it highly, that novel response gets reinforced. So the model can discover ways of answering that are actually preferred over anything in the demonstration data. It's no longer trying to match the teacher. It's optimizing directly for what people like. That's how you get better than the examples. But this freedom is dangerous and it needs a leash. If the policy is allowed to change without limit, chasing reward, it will drift away from the fluent, knowledgeable base model and start producing strange, broken text that happens to fool the reward model. So we add a crucial constraint. We penalize the policy for straying too far from where it started. In the objective, we maximize the reward, but we subtract a term, a KL penalty, that grows the more the model's behavior diverges from the original. Maximize reward minus beta times the distance from the base model. That leash is what keeps the model both aligned and coherent. And with that, the transformation is complete. Supervised fine-tuning taught the base model to act like an assistant. RLHF, guided by a reward model and held on a leash, refined it into an assistant people genuinely prefer. But this elegant machine has a dark side, some very real failure modes. And a responsible account has to look straight at them. Chapter 11, When Alignment Goes Wrong. RLHF is powerful, but it's also delicate and in some ways a little treacherous. Because the model is now optimizing hard against a reward model, an imperfect proxy for human judgment, all sorts of subtle failures can creep in. They are worth understanding because you've almost certainly felt some of them. The deepest problem is called reward hacking, and it's a classic trap in all of optimization. The model doesn't actually care about being good. It cares about scoring well on the reward model, and those are not the same thing. So if the reward model has any blind spot, any quirk, the policy will find it and exploit it ruthlessly. It learns to produce whatever superficially scores high, whether or not it's genuinely better. It's optimizing the measure, not the goal. The most familiar symptom is sycophancy. It turns out that human labelers, and therefore the reward model, tend to rate agreeable, flattering, confident-sounding answers a bit higher. So the policy learns to be a people pleaser, to tell you what you want to hear. To agree with you even when you're wrong, to pad answers with reassuring, confident language. If you've ever felt an AI was just a little too eager to agree with you, you were feeling reward hacking in the wild. There's another cost, sometimes called the alignment tax. In the very process of making a model more aligned, more cautious, more helpful in the measured way, you can sometimes make it slightly worse at raw capability. Overtuned models can become more likely to refuse harmless requests, more hedging, more verbose, less willing to be direct. Pushing too hard on harmless and pleasant can quietly erode helpful and sharp. It's that three-way balance again, and it's easy to tip. This is why the KL leash from the last chapter matters so much, and why the whole process demands enormous care. Push the optimization too hard, and you don't get a better assistant. You get a sycophantic, evasive one that games its own grader. The art of RLHF is applying just enough pressure to align the model, without so much that it starts hacking the reward instead of earning it. Balance, once again, is everything. So RLHF is powerful but perilous, a constant balancing act against a proxy that can be gamed. Its complexity, with a whole separate reward model and a delicate reinforcement loop, led researchers to a natural question. Could there be a simpler way to get the same benefit? And recently they found one. Chapter 12, A Simpler Path. Classic RLHF has a lot of moving parts. You train a separate reward model, then you run a delicate reinforcement learning loop against it, with all the instability that can bring. It works, but it's complex and finicky, so a natural question arose. Do we really need that whole apparatus? What if we could learn directly from the preference data and skip the separate reward model entirely? That's the idea behind a newer method called direct preference optimization, or DPO. The insight, and it's a genuinely elegant one, is mathematical. It turns out you can take the whole RLHF objective, the reward plus the KL leash, and rearrange it algebraically into a single, simple loss function that operates directly on the preference pairs. The reward model doesn't disappear exactly. It gets folded mathematically into the loss itself. In practice, this means DPO trains the model directly on the same comparisons. Response A is better than B, with one clean objective. It nudges the model to make the preferred response more likely, and the rejected one less likely, all while automatically keeping it from drifting too far from the base, just like the KL leash did. No separate reward model to train, no unstable reinforcement loop to babysit. Just a straightforward, stable training run on preference data. And this is why much of the field has been shifting toward DPO and its relatives. It's simpler, more stable, cheaper, and easier to get right, while achieving results comparable to full RLHF. It's a lovely example of how a field matures. First, a powerful but complicated method proves that something is possible. Then, someone finds the elegant core hiding inside it and makes it simple enough for everyone to use. The goal is unchanged: learn from human preferences. The path just got much smoother. So whether through classic RLHF or the newer DPO, we've now seen the full arc of alignment. Demonstrations, then preferences. But fine-tuning isn't only about turning a base model into a general assistant. The same machinery has other uses, and they're worth knowing about. Chapter 13, Fine-Tuning more broadly. Everything so far has been about alignment, turning a raw base model into a helpful, general-purpose assistant. But the same basic technique, gently continuing training on curated data, has other important uses that go beyond the 3 H's. The most common is specialization. You take an already aligned assistant and fine-tune it further on data from a specific domain to make it an expert. Fine-tune on medical texts and doctor-patient dialogues, and you get a model far sharper on medicine. Fine-tune on a company's own documents and support tickets, and you get an assistant that deeply knows that company. You're adapting a generalist into a specialist by showing it a focused slice of examples. But there's a practical catch. These models are gigantic, billions of parameters. Fully fine-tuning all of them for every specialized task is enormously expensive in computation and memory, and it produces a whole new giant copy of the model each time. For a long time, that cost put custom fine-tuning out of reach for most people. The breakthrough that changed this is a family of techniques called parameter-efficient fine-tuning, and the most famous is LORA. The idea is clever. Instead of updating all the billions of original weights, you freeze them completely, leaving the base model untouched, and you insert a small number of new, trainable parameters alongside them. You train only those tiny add-on adapters, often less than 1% of the total. It's like leaving a masterpiece painting untouched and adding your changes on a thin, transparent overlay on top. The effect is transformative for accessibility. Because you're only training a tiny fraction of the weights, fine-tuning becomes dramatically cheaper, faster, and lighter. You can create many small, swappable adapters, one for each task or customer, each just a few megabytes, all sharing the same frozen base model underneath. Parameter-efficient fine-tuning is a big part of why customizing these models is now within reach of individuals and small teams, not just the labs that can afford to train from scratch. And it's worth remembering the wider menu. If you just need the model to know a few current facts, you might not fine-tune at all. You might reach for retrieval from the RAG video. If you need to change its behavior a little for one conversation, a good system prompt might do it. Fine-tuning is the heavier tool for when you need to durably change how the model behaves. Choosing among prompting, retrieval, and fine-tuning is one of the real skills of building with these systems. Now, let's step back and assemble the whole picture. Chapter 14, The Complete Picture. Let's assemble the full pipeline of how the assistant you talk to actually gets made. It starts with pre-training from the last video. The vast, expensive process that grows a base model, a reservoir of raw intelligence that can complete documents but has no idea how to help. That's the raw material. Then comes fine-tuning in stages. First, supervised fine-tuning, learning from human demonstrations, which teaches the model the role, the format, and the habit of being a helpful assistant. It does most of the work. Then alignment from preferences, whether through the reward model and reinforcement loop of RLHF, or the simpler, direct approach of DPO, which refines the model into one that people genuinely prefer, going beyond what any demonstration could teach. And optionally further specialization, made cheap and accessible by techniques like LORA. And here is the whole thing in one sentence. The model you talk to equals pre-training, which supplies the knowledge and the raw ability, plus fine-tuning, which supplies the behavior, the alignment, and the purpose. Pre-training grows the mind. Fine-tuning gives it manners, a mission, and a moral compass. Neither is enough alone. The intelligence without the alignment is a wild, unhelpful genius. The alignment without the intelligence is polite but empty. It takes both. And the single most important idea to carry away is the one we opened with. Fine-tuning never added the intelligence. Every capability the assistant has, the knowledge, the reasoning, the fluency, was already grown during pre-training, sitting latent in the base model. Fine-tuning simply revealed it and pointed it at you. It took a reservoir of raw ability and carved a channel for it to flow through, in service of being helpful, honest, and harmless. And that completes the story of how a modern language model is made, from random noise through pre-training to a helpful assistant through fine-tuning. Everything else in this whole series, every agent, every tool, every prompt is built on top of exactly this. Thank you for going this deep with me across both halves of it. If it made the making of these models finally click, give it a like and subscribe, because next we open up attention itself, the idea at the very heart of the transformer. We're building AI up from the ground, one blueprint at a time. I'll see you there.